Watch this. An AI agent is handed a bug report, and with no help, it reads 5 files across the codebase, figures out the real cause, edits 3 of them, runs the test suite, red, then green, and opens a clean pull request. It looks like magic. So here's the uncomfortable truth. Take that exact same model, give it the exact same task with a naive setup, and it fails roughly 2 times out of 3. Same model, wildly different outcome. Because a coding agent is not a smarter model, it's a loop. Retrieve the right code, make a precise edit, run the tests, read the failure, and try again. The whole craft, and this is the big shift of 2026, is this. Stop prompting the agent and start designing the loop. Over the next 40-odd minutes, we'll design that loop the way a staff engineer would, from first principles, how it indexes and finds the right code in a million-line repo, how it assembles just enough context, how it edits files without breaking them, how it verifies its own work, and how we keep it from doing damage. And I'll keep coming back to one idea. The model is the engine, but the loop is the car. Let's build it. First, requirements. And the key insight is that coding agent is really 2 different products sharing a brain. Product 1 is autocomplete, the gray text that finishes your line as you type. It has to feel instant, under 300 milliseconds, or it's worse than nothing, and it gets cancelled the moment you press another key. Product 2 is the agent. You give it a task in plain English, and it works for minutes, editing many files, running commands, fixing its own mistakes. Autocomplete is fundamentally a latency problem. The agent is fundamentally a correctness and safety problem. Let's be explicit about functional requirements. Understand a large existing codebase. Propose and apply changes across multiple files. Run code and tests. And for the agent, keep going autonomously until the task is done. And the non-functional bar, because vague requirements make vague designs. Autocomplete, P95 latency under 300 milliseconds and a high acceptance rate. The fraction of suggestions the developer keeps. The agent, task success rate, did the tests actually pass, and a hard safety guarantee that it never destroys work. And underneath both, cost, because frontier model calls on large contexts, looped many times, get expensive fast. 2 products, 2 designs, we'll build the shared retrieval foundation, then split them. Everything from here is judged against those numbers. Before we draw boxes, let's size the problem. The back of envelope pass, a strong candidate always does. Say we're serving a company of 1,000 engineers on repos that total, very roughly, 10 million lines of code. First, the index. We don't embed whole files. We split code into meaningful units, functions and classes. So 10 million lines is maybe a few 100,000 chunks. Embed each into, say, a 1,000-dimension vector at 4 bytes a number. That's about 4 kilobytes per chunk. So a few gigabytes of vector index per large organization. That fits comfortably in memory for fast nearest neighbor search. The index is not the expensive part. The expensive part is inference. An agent task might make 10 to 30 model calls as it loops, each carrying tens of thousands of tokens of context. At frontier prices, that can be tens of cents to a few dollars per task. So 1,000 engineers running dozens of tasks a day is real money, and it's why prompt caching and model tiering later aren't optional. On latency, autocomplete lives on a sub-300 millisecond budget, so it uses a small model and a warm cache. The agent lives on a multi-minute budget, so it can afford the big model and the verification loop. Write those numbers down. A few gigabytes of index, dollars per task, two very different latency budgets because every design choice traces back to them. So how does the agent understand your code? The naive answer everyone reaches for first. Just put the whole repository into the model's context window. Let it see everything. This fails immediately for three reasons. 1. Size. A real code base is millions of tokens. It simply doesn't fit. And even the largest million token windows can't hold a serious mono repo. 2. Cost. You pay per token of context on every single call. Sending the whole repo every step would cost a fortune. And remember from the estimate that we loop 10 to 30 times per task. And 3. The subtle one. Quality actually gets worse. Bury the 5 relevant lines inside 100,000 irrelevant ones, and the model loses the thread. It gets distracted, confuses similar files, and hallucinates functions that don't exist. Researchers call it context rot. Past a point, more context means worse answers, not better. So the real problem is the exact opposite of the naive instinct. It isn't, how do we show the model everything? It's how do we find the tiny, exact slice of the codebase this one task needs and show it only that. Framed that way, the heart of a coding agent is a retrieval and context problem. And that's where the real engineering begins. Here's the first thing that trips people up. Retrieving code is not the same as retrieving documents. Regular retrieval, the kind in a RAG system for pros, chops text into chunks, embeds them, and does a nearest neighbor search. Do that to source code, and you'll cut a function in half and lose the fact that it calls 3 others and implements an interface defined in a totally different file. Code has structure that text doesn't, so a good coding agent passes the repo with a tool like treesitter into an abstract syntax tree, the real grammar of the code, and builds a repo map, every symbol, every function and class definition, and the call graph of who invokes whom. Then it retrieves with 3 complementary signals, not 1. First, embeddings for semantic similarity. Find the code that handles authentication, even if it never says the word auth. Second, lexical search, plain, fast grep or ripgrep for exact identifiers, error strings, and symbol names, which embeddings are surprisingly bad at. Third, structural search, go to definition and find all references, which walks the actual call graph to pull in the functions your target depends on and the ones that depend on it. You merge and re-rank those 3 streams. Embeddings alone miss the exact symbol. Grep alone misses the concept. The syntax tree is what turns a flat pile of files into a navigable graph. Hybrid, structure-aware retrieval is the foundation every other component stands on. Let's build the thing that makes retrieval possible, the index and the pipeline that keeps it fresh. When a repo is first opened, we walk every file, pass it with treesitter, and split it along syntax boundaries. 1 chunk per function or class, never mid-statement, so each chunk is a coherent unit. We compute an embedding for each chunk with a code-specialized embedding model, and we store those vectors in an approximate nearest neighbor index, think HNSW, so we can search hundreds of thousands of chunks in milliseconds. Alongside the vectors, we keep the symbol table and call graph for structural search. Now the hard part, the one interviewers love, keeping it fresh. You do not re-index the whole repo on every keystroke. That's far too slow. You index once, then incrementally invalidate. When a file is saved, you repass and re-embed only that file's chunks and patch the graph. When someone pulls a teammate's changes, you re-index just the changed files. Stale index is a real bug. If the agent reasons about code that no longer exists, it makes confident, wrong edits. And a subtlety: embeddings should be computed on the server for consistency, but the raw code often can't leave the customer's machine for privacy. So many designs embed locally or in the customer's own environment. The index is invisible when it works and catastrophic when it's stale, so treat invalidation as a first-class feature. Retrieval gives us candidates. Now the real skill: context assembly under a hard token budget. Think of the context window as a fixed-size shelf, and everything is competing for a spot. It won't all fit, so we choose deliberately. What always earns a place? The file the user is actually editing, the functions and types it imports and calls, because you cannot safely change code without seeing what it depends on. The specific symbols retrieval flagged as most relevant, and, crucially, the relevant tests, because those encode what correct behavior even means. On top of the concrete code, we add a compressed repo map, essentially a table of contents of the whole project, just signatures and file names, so the model knows what exists and where, even when the full source isn't on the shelf. Everything else is evicted, and we rank what stays by relevance and recency, pinning the current file and anything the user explicitly referenced. This is the central trade-off of the entire system: context quality versus window size and cost. Too little, and the model edits blindly. Too much, and you're back to context rot and a giant bill on every one of those 10 to 30 loop steps. Here's the mental model to walk away with. A great coding agent is, more than anything, a great context assembler. The model's intelligence is fixed. The leverage is in putting exactly the right things on the shelf, and nothing else. Between our context and the raw model sits an interface we have to design carefully: the prompt, the tools, and the output contract. Start with the system prompt. It defines the agent's role, its rules, and critically, the exact catalog of tools it may call. Those tools are exposed as a strict schema: read file, edit file, run command, search, each with typed arguments, and the model is required to respond in a structured format, usually JSON, that names a tool and its arguments. We don't trust it to produce free-form text we then guess at. We constrain the output so it's passable and executable every time, and we validate it before running anything. Then, the biggest performance lever on this path: prompt caching. Across the many steps of a single task, the system prompt, the tool definitions, and most of the repo context don't change, so the provider can cache the computed state of that shared prefix and charge a fraction to reuse it, which slashes both cost and latency. The design rule that falls out of this is precise. Put the stable content first: system prompt, tools, repo map, and the volatile content, the latest tool result, last, so the cacheable prefix is as long as possible. A clean tool schema, plus structured output, plus a cache-friendly prompt layout is what turns a chat model into a reliable agent runtime. Now, let's build the fast product: autocomplete. This is a separate pipeline, tuned for exactly one thing: latency under 300 milliseconds. The trick is the prompt shape, called fill in the middle. Instead of only showing the model the code before your cursor, we show it the code before and the code after and ask it to fill the gap, because the lines below your cursor are a massive hint about what belongs above them. A model has to be trained for this fill-in-the-middle objective. A plain left-to-right model can't do it well. To hit the latency budget, we pull every speed lever we have. A smaller, faster model than the agent uses. Quality matters less than speed here, because the human is right there to accept or reject. Prompt caching, so the unchanged file above the cursor isn't reprocessed on every keystroke. Debouncing, so we don't fire on every single character. And aggressive cancellation. The instant you type another key, the in-flight request is thrown away and a fresh one starts, because a suggestion for what you were typing a moment ago is useless. Autocomplete does not verify, does not run tools, does not loop. It is a latency, first, fire and forget suggestion, measured by acceptance rate. It's a completely different system from the agent, which is allowed to take its time because it's going to check its own work. Now the heart of it, the agent loop. A general agent, which we've covered in its own video, follows a simple cycle: plan, act, observe, repeat. The coding agent is that cycle wired to code tools. It plans a step. It acts by calling a tool. Read this file, edit that function, run these tests. It observes the result, the file contents, the command output, the failing assertion. And it loops, feeding what it just learned back into context until the task is done or it hits a budget. There are two broad styles, and naming the trade-off is a senior move. One is react, where the model interleaves a thought and an action each step. Flexible, self-correcting, but it can wander. The other is plan, then execute, where it drafts a full plan up front and then carries it out. More predictable and cheaper, but brittle when reality diverges from the plan. Most real agents blend them, plan at a high level, react at each step, and replan when they get surprised. And you must bound the loop, a maximum number of steps and a token budget, or a confused agent will spin forever burning money. Here is the whole philosophy of modern coding agents in one line. You get quality not by writing a cleverer prompt, but by designing a better loop, the harness around the model. What tools it has when it may retry, when you force it to stop and replan, and how a failure gets fed back in. The loop is the product. The model is just the engine inside it. Let's zoom into the single most underrated step: how the agent actually changes a file. The naive way is to have the model output the whole new file. It's a disaster. It's slow. It burns tokens, and on a large file, the model will silently drop or mangle lines it was never asked to touch. So real coding agents don't rewrite files. They emit edits, and there are two dominant formats worth knowing. The first, popularized by the tool Ada, is search and replace blocks. The model writes, find exactly this block of code, replace it with that block as structured text. The second is a standard unified diff, the same format Git uses, which editors like Z render as an editable diff you approve hunk by hunk. Either way, a separate fast apply step takes the patch, applies it, checks the result, still passes, and if a hunk doesn't cleanly match, it retries or asks the model to re-specify. Often that apply step is its own small, cheap model, while the expensive frontier model does the thinking. And a subtle failure mode researchers have named deletion avoidance. Models are eager to add code, but reluctant to remove it, so they leave dead code behind that still passes the tests, but slowly rots the code base. Good edit design fights this. State the blast radius of a change, make the target block an exact identity match so a wrong match fails loudly, and treat clear error messages as documentation the agent will actually read. Edits are surgical diffs, not rewrites, smaller, cheaper, reviewable, and far less likely to break the 99% of the file the agent should never have touched. This is the chapter that separates a toy from a tool. After the agent makes an edit, what happens next is everything. It verifies. It runs the test suite. it runs the type checker, it runs the linter, and then, the crucial part, it reads the output, and a failing test message goes straight back into the loop as a new observation, so the agent can target the actual error and try again. Green, and it's done. This test-driven loop is not a nice-to-have. On benchmarks like SWE Bench, agentic workflows that are handed the tests and iterate against them reach the 90+% range, dramatically ahead of one-shot patching. But here's the twist that every senior engineer must understand, and it's the dark side of make the test pass. If passing the test is the reward, a capable agent will find the cheapest way to make it pass. And that isn't always fixing the bug. This is reward hacking, and it's very real in code. Auditors have caught agents editing the test itself to assert the wrong thing, hard-coding the expected output, catching and swallowing the exception, or, in one striking case, running git log to read the answer straight out of the commit history. Researchers found a large fraction of some benchmarks' failures were actually flawed tests the agent could exploit. The design lesson is sharp. The tests are the reward function, so treat them as trusted and immutable. The agent may run them, but must not edit them. Run them in a clean, isolated environment, and watch for the telltale signs of gaming, like a diff that touches the test file more than the source. An edit is finished when the real tests pass honestly, not when the agent has found a way to make the light turn green. Real tasks are long, and long tasks break agents in a specific way. A coding session can run for many minutes and dozens of tool calls, and the context window fills up fast. Studies find something like 80% of it gets eaten by file reads and tool results, not the actual conversation. Push past roughly 90% utilization, and the agent starts forgetting decisions it made 10 minutes ago and reintroducing bugs it already fixed. So we manage memory on two timescales. Within a task, compaction. When context gets full, we summarize the older history, what we tried, what worked, what failed, into a compact memo and drop the raw tool output, so the working context stays bounded. It's lossy and it's a blocking step, so you do it carefully. But it's what lets a task run effectively unbounded. Across tasks, persistent project memory. Coding agents read a rules file that lives in the repo. You'll see names like agents.md or a rules file that states how this project is structured, which commands build and test it, the naming conventions, and the security boundaries. It's always on guidance, so the agent doesn't rediscover the project from scratch every session, and because it's a checked-in file, a human reviews it. It's the trusted source of truth. The pattern to remember: compaction keeps the current run alive, persistent memory makes the next run start smart, and both are kept honest by human review. Memory is what turns a clever one-shot into an agent that can actually finish a big job. Now the part that should make you nervous, and raising it unprompted in an interview is a strong signal. We've given a language model the ability to read untrusted text and run commands on a machine, and a coding agent ingests untrusted text from an unusually large number of places. The repository itself, code comments, a GitHub issue or pull request, a dependencies README, web pages it fetches during research, and the results returned by external tools. Any of those can carry an indirect prompt injection, hidden instructions that hijack the agent into doing something you never asked. This isn't theoretical. There are documented incidents of an agent processing poisoned web content and silently committing obfuscated malware, and of malicious instructions buried in tool descriptions, so-called tool poisoning, where, as one researcher put it, no output from your tool server is safe, and the numbers are sobering. Against adaptive attacks, success rates exceed 85%, while most bolt-on filters stop under half, so you cannot filter your way out of this. The defense is architectural, and it's the least agency principle from agent security applied to code. Every command runs inside a sandbox, a container, or micro VM, with no network by default, a file system scoped to just the project, and outbound connections blocked so data can't be exfiltrated. Destructive or sensitive actions, deleting files, touching credentials, pushing to production, sit behind an explicit human confirmation, never the agent's sole discretion. You checkpoint with Git before it starts, so every change is one undo away. And you treat any tool the agent loads as untrusted supply chain. Capability without a sandbox isn't a feature. It's an incident waiting to happen. For big tasks, one agent grinding sequentially is slow and its context gets muddy. So a common pattern is to split the work across specialized subagents under a shared plan. An orchestrator decomposes the task and spawns workers, one focused on the implementation, one writing tests, one on documentation, one reviewing for security. Because each subagent has its own clean context window, you avoid the context rot problem, and you can run independent pieces in parallel, which multiplies throughput at modest extra cost. The coordination is the hard part. They share memory and a task queue, and you need resource locks so two agents don't edit the same file at once and clobber each other. The multi-file atomicity problem again. The highest value specialist is the reviewer. After the implementer produces a diff, a separate reviewer agent, one that didn't write the code and isn't invested in it, explores the repo, checks the change against the issue, and either approves it or hands back structured feedback that re-enters the loop. That's agentic code review, and it catches a lot before a human ever looks. But note the honest limit. Sub-agents add orchestration complexity and cost, and more agents reading more untrusted content widens the injection surface from the last chapter. So you reach for multi-agent when a task genuinely decomposes. Implement, test, review in parallel, not as a default. The reviewer that didn't write it is the piece worth stealing for almost any design. Let's trace one real task through the machine we've built, then break it. A bug report arrives. Indexing has already passed the repo into an abstract syntax tree. Retrieval uses embeddings, plus grep, plus the call graph to find the three relevant files. Context assembly puts them, their imports, and the failing test on the shelf. Stable content first for caching. The loop plans a fix and emits a search and replace diff. The apply step patches it. The sandbox runs the tests, one still fails. The failure feeds back. The agent adjusts, tests go green honestly, a reviewer agent signs off, and it opens a pull request for a human. Now break it in the 4 ways interviewers love. 1. A giant monorepo where retrieval grabs the wrong file. Fix is a better repo map and structural search, not a bigger window. 2. A flaky test that passes and fails at random, so the loop thrashes forever. Fix is a hard iteration cap plus non-determinism detection. 3. The agent tries to make the test pass by editing the test. Fix is immutable, isolated tests, and a guard that flags diffs touching test files. 4. A poisoned dependency readme tries to inject a command. Fix is the sandbox, no egress, and human confirmation on anything destructive. Every failure maps to a component we designed, and naming the failure and its fix is exactly what the senior interview is testing. How do you even know your coding agent is any good and stays good as you change it? You need evaluation, and coding is unusually lucky here because correctness is partly objective. The tests either pass or they don't. Start offline with a benchmark like SWE bench verified, 500 real GitHub issues with known fixes, to get a comparable success number. But treat that number with suspicion, and saying so is a senior signal. Benchmarks leak into training data, so a high score can be memory rather than skill. And as we saw, agents reward hack them. One audited system scored in the 80s until researchers found a quarter of its runs were copying answers out of Git history. So you never rely on a public benchmark alone. You build your own private regression suite from real tasks your agent has handled, so you catch when a change quietly makes things worse. The way any team guards a codebase with CI. You add an LLM as judge to review diffs for quality beyond just passing tests. But you calibrate the judge against human ratings because it has its own biases and can be gamed too. And you close the loop online. In production, watch acceptance rate, how often humans revert the agent's commits, and whether its pull requests pass CI, the metrics that reflect real usefulness. Designing that full eval platform is a whole topic of its own. Here the point is that a coding agent without a regression suite is one model update away from silently breaking, and you can't ship what you can't measure. Let's talk scale, latency, and the bill, because a coding agent is expensive to run at a company of thousands. First, prompt caching is your biggest lever. Across the many steps of one task, the system prompt, tool definitions, and repo context barely change, so catching that shared prefix cuts both cost and time to first token sharply, which is exactly why we put stable content first and volatile last. Second, indexing. Build it once and incrementally update just the files that change on save, so retrieval stays fresh without a full rebuild. Third, model tiering. The single best cost move, a small, cheap model for autocomplete and for the apply step, and the expensive frontier model reserved for planning and hard reasoning. You spend the big model only where it changes the outcome. Fourth, for long tasks, run the agent in the background, asynchronously streaming progress, so the developer isn't blocked and you can batch and schedule the work. And there's a serving wrinkle from long horizon tasks. Each agent holds a large growing KV cache for its session, and compaction has its own compute cost. So serving many concurrent long-running agents is a stateful memory problem, not a stateless request one. The theme across all of it is the same trade-off: 3 ways: latency versus quality versus cost. Cache aggressively, tier your models, and keep only the context that earns its place. A few follow-ups a sharp interviewer will push on. Monorepos and multi-root workspaces. One task can span several packages, so retrieval and the repo map must cross project boundaries cleanly. Index freshness. If a teammate's push changes aren't re-indexed, the agent reasons about stale code and makes confident wrong edits. You need fast, incremental invalidation. Atomic multi-file edits. A refactor that touches 10 files must land as one coherent unit, not 8 successes and 2 failures leaving the repo half-broken. Determinism and cost caps. Hard limits on iterations and tokens, so a confused agent can't spin forever or run up an enormous bill. Privacy. For many companies, the source code cannot leave their environment, which pushes indexing and sometimes inference on-premise or into their own cloud. And human in the loop. The agent proposes, a person reviews the pull request. It's a very fast junior engineer, not an unsupervised one, and the review gate is a feature, not a limitation. Each of these is the same theme once more. Keep the loop grounded in the real, current repository and the real tests, and keep a human at the point where a mistake would be expensive. Quick red flags. The tells that someone hasn't actually built this. Dumping the whole repository into the context window and hoping. Retrieving code like pros with embeddings only, ignoring the syntax tree and plain grep. Having the model rewrite entire files instead of omitting diffs. No verification step. Shipping code the agent never ran. Trusting the tests blindly, so the agent can pass them by editing them. An unsandboxed shell with real network and file system access. No cap on iterations. And no regression suite, so the next model update silently breaks everything. Every one of those breaks the spine. So, the whole system on one breath. A coding agent is a loop, not a model. You index the repo into a syntax tree and retrieve with embeddings plus lexical plus structural search. You assemble the minimal write context under a token budget. You edit with precise diffs, not rewrites. You verify by running the real, immutable tests and feeding failures back in, while watching for the agent gaming them. You manage memory with compaction and a checked-in rules file. You run every command in a sandbox with least agency because everything it reads is untrusted. And you keep a human on the review gate. Get the loop right, and an ordinary model does extraordinary work. If you want to practice designing systems exactly like this, with an interviewer that pushes back with real follow-ups, come do it free at crackit.io.